We'll consider the example of the monomial functions. So here, un is going to be just x to the power n, and this will be defined on the interval from 0 to 1. And we'll look at this sequence of functions and ask the question of, does un converge to 0? And as I just said in the last video clip, it all depends on what mode of convergence we specify. So we'll look at the different types of ways that this sequence could possibly converge. And so just to make things a little bit more concrete, let's take a look at these functions. So u1 is going to be the function x. u2 is going to be a parabola. Whoops, let me draw that a little better. There we go. So there's u2, and then u3 is going to be cubic, u4 quartic, quintic, etc. So we have u2, u3, carrying on this way, right? So that's the collection of functions that we're looking at. And so as you see, it looks like these things are getting closer and closer to 0. So let's ask the question, do these things converge to 0 pointwise? So for pointwise convergence, we start by fixing a point or fixing a coordinate. So we fix the coordinate x in our domain here, and then we look at what's going on with the xth coordinate of un, and the xth coordinate of un is just going to be x to the n. Actually, you know what? Here, maybe this would be a little bit more convincing if I picked something that looks like a fixed value. So xi is a fixed value. It is a chosen coordinate. It's this one right here. Okay. Now, if I look at this guy and I raise this to some increasingly higher power, it is going to go to 0 as n gets big. Since we have that it's between 0 and 1. And there's some theorem in mathematics that says if you take any number that's less than 1 in absolute value, then when you raise it to a high power, it goes to 0. Okay, so what this tells us is that, so since this argument is true for any fixed choice of xi, that means that un converges to 0 pointwise. All right, so now let's consider a different mode of convergence, a different topology. Let's say L2. Okay, so this time we're going to be looking at the distance from un to the 0 function in the L2 metric. So this is going to be the square root of the integral from 0 to 1, because our domain is 0 to 1. And we look at the magnitude squared of this function. We integrate that, and after integrating, we take the square root. All right, so that's how we compute the distance from un to 0. Maybe just to emphasize that we're looking at the convergence to 0 here, let me just show that that's the same right there. Okay, so for our particular function, we're integrating from 0 to 1, x to the 2n dx, which we can do explicitly. Oh, and then we take the square root. And so this is going to be the square root of 1 over 2n plus 1. And that fraction, you can tell, goes to 0 as n goes to infinity. Okay, so then the conclusion is that un converges to the 0 function in L2. And let me just point out while we're here that since it's the case that un converges to 0 if and only if its square converges to 0, most of the time people just work with this one because it's simpler, because then you don't have to have these square roots, and it makes the calculations a little easier. So in general, from now on, I'll leave off the square root, but it's not because I'm wrong, it's because I'm lazy. The last mode of convergence that we have to check is uniform convergence. So now, let's see. Now it turns out that this sequence does not converge uniformly. And so to see that, well, we have to show that I can make all of the coordinates less than some epsilon tolerance simultaneously, right? So what does that look like in the current picture? So if we look at a plot of this again, oops, and now I done messed it up. There we go. So suppose we want it to be the case that the tolerance is this epsilon. So can I make all of these xn's simultaneously within this distance epsilon from the 0 function here? Well, the answer is surely not, because if I look at if that were the case, then there would be some n such that un is entirely within this orange tube after that point in the sequence. And this doesn't happen, because you can see that no matter how big of an n I choose, there's going to be some latter part of the function that pokes out above the epsilon window. So all of these guys, they've got some little bit jumping out, and that means that the entire thing is not inside the epsilon window because it pokes out over here. So this is bad. And that always exists. So let me just write this down with a bit of notation. So let epsilon be, say, 1/2. Pick your favorite number, doesn't matter. For any choice of n, there are points in the interval with x to the n greater than 1/2, and so that means that the maximum difference between xn and 0, yeah, let's again choose these to look specific. I can choose a point c with cn bigger than 1/2. So if I take the max over all x's, no, I had that right before. It's at least going to be as big as that one, which is bigger than 1/2. And so then this tells you that the max of the difference does not go to 0. So it does not converge uniformly on this interval. Let me take this moment to point out that it is important to specify the interval when you're talking about uniform convergence. Uniform convergence is defined in terms of a particular domain. So when you talk about uniform convergence, you have to specify what domain the sequence is or is not uniformly converging on. So to give you an example of that, for this one, we just looked at the functions xn on the domain from 0 to 1. But if I'd instead chosen the functions xn on the domain from 0 to 1/2, or 1/2, whichever, how do things differ? Well, now let's take another look. And so I have this one and so forth for this sequence of functions. But now I'm only looking at this domain from 0 to 1/2 right here. So my view of the world is restricted to just what's in this blue window. So forget about anything outside of this window. I'm just looking at the interval from 0 to 1/2 right now. And now look at what happens. The maximum value of xn minus 0, so the maximum coordinate difference, happens right here on the left endpoint. So in other words, the furthest that this purple line gets from this green line down here occurs at the right endpoint of the interval, and the furthest that this orange curve gets from the green line occurs right here. So this is maybe the max of x n plus 1, right? So go further down the sequence, and so on and so forth. And so the purple guy is everywhere under this line. The orange guy is everywhere less than or equal to this line right here, and so on and so forth. So now I can eventually, if somebody says, yeah, I want everything to be within this epsilon of the green line down at the bottom, if I go far enough, I can make sure that it's entirely under there. So in fact, xn converges to the 0 function uniformly on the interval from 0 to 1/2. So different questions have different answers, and it depends on the domain that you're looking at.